It is remarkable when one looks closely how nature builds its most magnificent structures from the simplest of rules. Consider the humble fern. Each frond is a miniature replica of the entire plant, and each leaflet upon that frond is a smaller copy still. This elegant principle of self-similarity, where a pattern repeats itself at ever-decreasing scales, is a hallmark of the natural world. We see it in the branching of a mighty oak tree, reaching for the sky with limbs that fork and divide in the same way its trunk first split from the ground. We see it in the jagged, intricate coastline of a continent, which reveals the same rugged complexity, whether viewed from space or from a few feet away. This is the essence of a fractal, a shape that is infinitely detailed, endlessly repeating. Nature, it seems, is a master artist of repetition and recursion. This underlying code is not merely for show, it is a profoundly efficient method of construction. A tree does not need a unique blueprint for every single twig. Instead, it follows a simple recursive instruction: grow, branch, and repeat. This allows for immense complexity to arise from a very small set of rules. The same can be said for the delicate, six-sided symmetry of a snowflake, where crystalline structures build upon one another in a repeating fractal pattern, ensuring no two are ever precisely alike. Yet all adhere to the same foundational geometry. It is a system of boundless variety born from disciplined repetition. This is nature's genius, a strategy perfected over billions of years of evolution, creating robust and resilient forms that are both beautiful and functional. From the spiraling arms of a galaxy to the intricate network of veins in a leaf, these patterns are everywhere. They are a universal language, speaking to a fundamental order that governs processes both vast and minuscule. Even the lightning that flashes across a stormy sky traces a fractal path, seeking the ground through a cascade of branching channels. It is as if the universe itself has a preference for this kind of structured complexity, finding it the most effective way to distribute energy, to grow, and to connect disparate points. Observing these phenomena, one cannot help but feel a sense of wonder at the interconnectedness of it all, a grand design woven into the very fabric of existence. And so we must ask ourselves a critical question. If nature employs this fractal logic to build the physical world with such breathtaking efficiency, could it be that information itself follows a similar architecture? Could the streams of data that now define our modern world, the digital equivalent of rivers and lightning bolts, also possess a hidden, self-similar structure? Perhaps our current understanding of information as a simple, linear sequence of ones and zeros is akin to seeing only the trunk of the tree, missing the magnificent branching canopy that constitutes its true form. This is the tantalizing possibility that stands before us, a new frontier in our quest to understand the world. For decades, our approach to information has been guided by a beautifully simple yet ultimately limited idea. The pioneering work of Claude Shannon taught us to see information as a sequence of bits, a one-dimensional line of data. This model measures uncertainty and randomness, and it has served as the bedrock of our digital age. It has given us the tools to send messages across oceans and to store vast libraries on tiny chips. However, it views information as fundamentally flat. It does not account for the rich, multi-layered structure that seems so prevalent in the natural world. It is a powerful language, but one that may not be telling the whole story. It is like describing a symphony by merely listing the notes without acknowledging the melody, harmony, or rhythm that gives it meaning. Fractal Information Theory, or FITi, offers a profound alternative. It proposes that information is not always a straight line, but is often structured like that fern or that tree. It is inherently fractal. According to this view, a piece of information, such as an image or a sound file, contains patterns that repeat at different scales. A high-resolution photograph of a mountain, for example, is not just a random collection of pixels. The craggy texture of a large rock formation might be echoed in the texture of a small pebble within the same image. FIT suggests that the information itself is self-similar, with large-scale structures mirroring small-scale details. It presents a world where data is not just a stream, but a landscape filled with recurring features. This shift in perspective has staggering implications. If information is indeed fractal, then we have been handling it rather inefficiently. By treating it as a linear sequence, we are forced to describe every single detail from scratch. But with FITi, we can take a more intelligent approach. Instead of storing the entire sprawling structure, we need only store the initial pattern and the simple rule of how it repeats. This is the heart of fractal compression. It allows us to capture immense complexity within a tiny amount of code, much like how DNA encodes the entire plan for a living organism. It is a move from brute force description to elegant systemic understanding. This is not merely a theoretical curiosity. It is a new lens through which we can see the hidden order in the digital universe. It suggests that nested within our data are recursive relationships and dependencies that traditional methods simply overlook. Whereas Shannon's theory is excellent for measuring the surprise or newness in a signal, FITi is designed to find and leverage the inherent structure and repetition. It does not seek to replace the old models, but to complement them, giving us a more complete and holistic understanding of what information truly is. It allows us to appreciate not just the content of a message, but its intricate, multi-layered architecture. The consequences of this new understanding are not confined to the abstract realm of theory. They are already beginning to shape our technology in tangible and exciting ways. Consider the challenge of streaming high-definition video over the internet. To send such a vast amount of data smoothly requires immense bandwidth. Fractal compression, however, changes the game. By identifying and encoding the self-similar patterns within and between video frames, the texture of a fabric, the branching of a tree in the background, it can reduce the file size dramatically without a perceptible loss in quality. This means clearer, more reliable video streams that use a fraction of the data, making high-quality content accessible even with limited internet speeds. This principle extends naturally to data storage and recovery. Imagine a digital archive that stores information fractally. If a portion of the data becomes corrupted or lost, we are not left with a meaningless whole. Because the information is self-similar, it may be possible to regenerate the missing pieces by extrapolating from the patterns that remain at different scales. A small, intact fragment could hold the key to reconstructing a much larger section, much like how a botanist can identify an entire tree from a single leaf. This creates a form of data storage that is inherently resilient and fault-tolerant, a critical feature in an age where we entrust so much of our knowledge to fragile digital systems. Beyond storage, fractal information theory is poised to revolutionize artificial intelligence. A persistent challenge in AI is creating a memory system that is both efficient and flexible. The human brain does not seem to store memories as simple, isolated files. Our recollections are interconnected and multi-layered. FIT provides a model for an AI memory that works in a similar way, storing information in a nested recursive structure. An AI could access a memory at a high level for a quick summary or zoom in to retrieve incredibly fine details. This would allow machines to learn and reason in a more contextual, human-like manner, understanding the relationships between concepts rather than just processing isolated facts. This fractal approach could even lead to entirely new forms of computer hardware. We are now exploring the frontiers of quantum computing, where the laws of physics themselves become part of the calculation. The intricate, probabilistic nature of quantum states exhibits a kind of complexity that resonates deeply with fractal geometry. By designing quantum algorithms and memory systems based on FIT, we may unlock computational powers that are currently unimaginable. From managing the colossal datasets of genomic research to building more adaptive robots, the practical applications of this theory are as diverse and far-reaching as the fractal patterns we see in nature itself. The revolutionary ideas of fractal information theory do not stop at the boundaries of our digital world. They invite us to look deeper, to question the very nature of physical reality. The universe, at its most fundamental level, is a realm of information. The laws of physics can be seen as the rules that govern how this information is processed and transformed. If information is inherently fractal, then it stands to reason that the physical laws themselves might possess a similar multi-scale structure. This suggests a profound unity, a world where the same organizational principles that shape a coastline also govern the interactions of subatomic particles. This perspective offers a compelling bridge between the seemingly disparate worlds of the very large and the very small. In quantum mechanics, particles exist in a state of potential, a cloud of probabilities. This complex, layered uncertainty has qualities that are strikingly fractal. Similarly, in cosmology, theories like the Tavari field propose that space-time itself is not smooth, but has a granular, intricate structure at the smallest scales. FIT provides a framework for unifying these ideas, suggesting that the complexity we observe at every level of the cosmos is a manifestation of an underlying fractal information field. It is a vision of a universe that is self-similar all the way down and all the way up. In our daily lives, we are confronted with an unprecedented flood of information. We are drowning in data, struggling to find meaning in the noise. Fractal information theory offers us a lifeline. It teaches us that within this overwhelming complexity, there is a hidden order. It gives us a tool not just to manage information, but to understand it. By learning to see the repeating patterns, the self-similar structures, we can begin to make sense of the chaos. It is a skill that is becoming essential for navigating the modern world, allowing us to identify the core ideas within a sea of detail and to see the connections between seemingly unrelated events. Ultimately, this is more than just a new scientific theory. It is a fresh way of seeing, a new philosophy for an information-saturated age. It reconnects us to the wisdom of the natural world, reminding us that the most complex systems are often built from the simplest rules, repeated with infinite patience and variation. It shows us that the architecture of a tree and the architecture of knowledge may not be so different after all. By embracing this fractal view, we not only improve our technology, but we also deepen our appreciation for the intricate, beautiful, and profoundly interconnected world in which we are privileged to live.